Good morning, chemistry classes. This is Mr. Barone. It's March 20th. It's about 8:50 in the morning. Just a reminder, Castle Learning is due at midnight tonight. Much better job yesterday. I'm starting to see on Castle Learning that a large number of you guys have started it. A decent number of you guys have actually finished it. So keep that going. You have about 15 hours left to get it done. So like I said, please work on that, finish it up, and I will be marking off the grades probably over the weekend or first thing Monday morning. All right, moving on. We are in as you can tell, I'm making this video. This is probably Wednesday's lesson. I'm making it on Friday today. So we will be probably covering this by the middle of this upcoming week, probably Wednesday. Here is your do now. Take a minute, look at these three questions that are one after another on a recent Regents exam. Take a minute, try to answer them, and we'll go over it. So I'm going to pause the video right now. All right, welcome back. I liked these three questions. I know I always want to do like one question and just let you guys work on it so we can get through it. But these are your review questions. This is your Regents review. We're going to spread out Regents review throughout the entire year by these do now questions, so they are very important. So number 34, what is the chemical name of the compound? It looks really scary, but hopefully you recognize that there are two substances or members of table E in this formula. NH4 and SCN, they both appear on table E. I should be able to jump over there and keep you guys with me. If I go through my reference table, I'm gonna counterclockwise, you see that they are both here. So NH4, it's called ammonium. And SCN is also here. I'm not going to switch colors. SCN is right here. And you should remember that we never, ever change the name of polyatomic ions. So therefore, NH4SCN should simply be ammonium thiocyanate. And let's see if that is in fact one of your answer choices. Ammonium thiocyanate, number 1 will be your answer, okay? So the answer to that one is number 1. Number 35, which equation represents a conservation of atoms? This is a conservation of mass question. When you see this phrase, conservation of atoms, it's saying which one of these is balanced. So let's go one by one and let's see which one is balanced and which one is not. I have 2 Fe's and I have 2 Fe's on this side. So far, so good. I have 2 times 2 is 4 oxygens on the left, but I have only 3 oxygens on the right. That's not going to cut it. That is not balanced. I have 2 Fe's on the left. I have 2 Fe's on the right. I have 3 times 2 is 6 oxygens on the left, and I still only have 3 oxygens on the right. That one is not balanced. I have 4 Fe's on the left. 2 times 2 is 4 Fe's on the right. I have 2 times 2. I have 4 oxygens on the left, but I have 2 times 3 is 6 oxygens on the right. That one's not balanced. Okay, and lastly, hopefully, fingers crossed, this is the right one. 4 iron atoms on the left. 2 times 2 is 4 iron atoms on the right. 3 times 2 is 6 oxygens on the left. 2 times 3 is 6 oxygens on the right. That one is balanced. That is your answer. And last but not least, number 36, which compound has covalent bonds? If you're text coding, covalent bonds happen between non-metals. So in other words, which one of these feature 2 non-metals bonded together? H and O, those are both non-metals. That could be our answer. Lithium and oxygen. Lithium's a metal, oxygen's a non-metal. That is ionic. Sodium is a metal. Oxygen is a non-metal. That's ionic. Potassium is a metal. Oxygen is a non-metal. That's ionic. So number 1 is going to be H2O. Hydrogen is a non-metal. Oxygen's a non-metal. When they bond, it is covalent. All right, there's your do now. Let us move on. Let's see if I can slide this over here. Okay, our objectives for the day: to create a definition for equilibrium. And we're also going to verbally and in writing describe what is happening at the molecular level in terms of rate and concentration for a system at equilibrium. It's a lot of new words there. We will get to it. Here's your joke of the day. That's right. I am wearing moccasins and pajama pants. Check it out. I'm actually wearing moccasins. See that? Eh? Living the dream. All right. So here we go. Here's your first turn to talk. I want you guys to take a minute and check it out. When you hear the word equilibrium, what comes to mind? What does it mean to a chemist? What is an example of something in equilibrium? I'm going to pause the video. Think about this word. I know you've probably heard it in living environment, maybe in earth science. Think about what you know about equilibrium. All right. Hopefully you had some time to think about it. We're going to give you the definition in chemistry in a minute. All right. So equilibrium, here's a picture of something at equilibrium. It doesn't probably mean much to you just yet, but you should notice that when we're talking about equilibrium, we have a lesson from earlier this week. It has this double arrow. So this double arrow is going to deal with something at equilibrium, okay? And so keep that in mind. And as I give you guys the definition here in a minute, just keep in mind that when you're talking about something at equilibrium, you will oftentimes see this double arrow, okay? So just keep that in mind. All right, moving on. I'm just going to skip this and go right to the definition that you will need to know. So our definition of equilibrium in chemistry is this. You will absolutely need to know this word. This comes up on every single Regents exam. They will ask you to define it, or they will ask you to apply this definition. So to chemists, equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. In other words, when the speed at which the reaction going from reactants to products equals the rate or the speed at which products are turning back into reactants. Okay, it's as simple as that. And we're going to talk about what that means. So take a minute, I'll pause the video, copy that definition down. Okay, welcome back. Hopefully you copied that down. Now, like I said, this is, to go back to my earlier slide, equilibrium is a word you know from living environment. You typically know equilibrium. It features that like prefix like equal, like the same, or you know, it's almost like equilibrium and homeostasis. Those are words that you guys remember from living environment. So some students usually have a pretty good handle as to what equilibrium might mean. And it does sort of mean equal. But what students usually mix up is what is equal. And I highlighted it in yellow. It's the rate of the reactions are equal, not the concentrations, not the volumes. Nothing else really matters except for the rate. How fast the reactants turn to products. And that will equal, at equilibrium, that will equal how fast the products turn back into reactants. So we're going to talk about the implications for this. Let's look at a quick thought experiment. Take a minute, read this question, okay? Or this problem, I should say. This is a story of two wet towels. So you have a wet towel. One is hanging out on a line out in the sun, and another wet towel is stuffed in your duffel bag after being used at the gym. So they're both wet. Towel A is wet, towel B is wet, but towel A is hanging up on a line, whereas towel B is zipped up in this duffel bag. So think about that, okay? Answer these three questions in your head. I'm going to pause the video. I want you to read these three questions. Think of an answer in your head. Maybe copy down some notes in your notebook. We're going to go over it. All right, welcome back. You probably had some time to think about it. You probably know the answer to number one. Most of you guys are probably going to say, obviously, Mr. Barone, the towel that's outside in the sun is going to dry faster, maybe in a few hours. And that wet towel in the gym bag might not dry at all so long as it's in the bag. It might get all moldy and gross. For number two, why? So I would still imagine that a lot of you guys probably have an idea. Well, the towel A out in the sun, it has some heat from the sun. It has fresh air to I don't know, maybe you guys don't understand exactly why the fresh air thing works, but maybe it has space to evaporate, right? All of a sudden those water molecules can leave. Whereas when they're in the gym bag, they can't. They don't have that fresh air to scoop up those water molecules and let them dry off and fly off and leave the towel. They're stuck in there. So what is happening at the molecular level? That's where we get to this idea of equilibrium, okay? And that's why the two examples of the wet towel out in the sun, towel A, is in what's called an open system, meaning those water molecules are free to leave the towel. But when they're in the duffel bag, they are in a closed system. And that's going to be what we're going to watch in a minute. When you're in a closed system, when that duffel bag is zipped up and they're in a closed system, now those H2O molecules that are the trillions and trillions of those H2O molecules that are on that wet towel in that duffel bag are not allowed to escape. They're in a system and they will reach what's called equilibrium. We're going to talk about what that means with these two videos. So to try to do this right, you will see on this post, I will have told you guys to watch these videos in the middle of this video. So I'm going to ask you to pause this video and I want you to watch these two videos. The first link, make sure you get the right one. It should talk about the two towels. Okay, it should feature a flashlight and a molecular look at what's happening to these wet towels. Make sure you watch that video first. Watch the whole thing. The second video, it's a longer video. It's kind of confusing. You can fast forward to the 10-minute and 30-second mark and watch the two examples of the people throwing apples over the wall. Trust me, it should make some sense. Remember, as you watch these videos, you're thinking about the rate of the forward reaction equaling the rate of the reverse reaction and how it applies to this example. So I'm going to pause my video. Okay, you can minimize this and go watch these two videos. For that second video, fast forward to 10 minutes and 30 seconds. All right, go. All right, welcome back. Hopefully you watched those two videos. I probably could find a way to play them for you and narrate over them, but that'd be a lot of talking and video watching at the same time. So I'm just going to trust that you watched it. It will help you understand this, but I'll sort of describe it to you as well. So for this first video, you saw that what happens is towel A out in the sun, the liquid water molecules that are on the towel that make it wet are free to turn into the gas molecules, like water in the form of gas, and they're free to just go off into the sky and out into the atmosphere, and they disappear. They leave the towel. They are allowed to leave. They essentially evaporate away from the liquid phase to the gas phase. However, the interesting one that we're going to be talking about is the towel in a bag. As those liquid water molecules in the wet towel leave the towel, they turn into the gas phase, they have nowhere to go, and there becomes so many gas molecules of water that they eventually will actually go back into the liquid phase. So what happens is that towel does not really ever dry because it's in a closed system. You have all those water molecules sealed up in that bag, and it reaches what's called an equilibrium. And this is what I need you to understand. It's not that that nothing's happening in the towel, right? It's not that suddenly everything stops and they're no longer turning into the gas phase. Here's the part. The water molecules on the towel that are liquid, that turn to gas, that's happening at the same speed as the gas molecules are falling back into the towel. So what happens is the liquid is turning to a gas as fast as the gas is turning to a liquid, and it reaches equilibrium, meaning there is no net change in how wet the towel feels, but there is still plenty of stuff happening at the molecular level. And I'm going to say that one more time. The rate of the forward reaction is equaling the rate of the reverse reaction. So the rate at which the water is going from liquid to gas is equal to the rate at which the water molecules are turning from gas to liquid. So you no longer see any change in the amount of liquid and gas in the towel, in that bag with the towel in it. So if you go back to the second video, that's why it's a simplified version of it. When you have the two people throwing apples over the wall, right? Well, when one person starts throwing it faster, but suddenly they start to equal the same rate. When they throw the apples over the wall at the same speed, the piles of the apples don't change, right? Because as one person throws the apple over the wall, the other person does the same at the same speed. So the size of the piles stops changing. And that's what equilibrium is, right? The amounts of reactants and products will stop changing when you're at equilibrium. Okay, and so one last distinction that's really important here is that if you look at that video of the piles of apples, notice that when it's at equilibrium, the piles of apples are not equal. The size of the pile, there's one side of the piles of apples on one side of the wall is bigger than the pile of apples on the other side. That's okay. The concentrations or the amounts do not need to be equal. When the rates are equal, the rate at which they're throwing apples over the wall, once the rates are equal, it's at equilibrium. And notice that it's not that the concentrations or the piles of apples are the same. It's the rate at which they're being thrown over the wall is the same. So what we say is that when we're at equilibrium, the rates are equal and the amounts are constant. So the amounts of apples on both sides of the wall are constant, not equal. But the rates of the apples being thrown over the wall are equal. All right, we will keep practicing that. But that is the biggest thing that you need to know about equilibrium and today's lesson. All right, so let's take a minute and let's ask what you're going to be, let's take a minute and let's see what you're going to be asked to do to answer questions like this. So why don't you read this question and describe what's happening here. If this is at equilibrium, describe to me in your own words what you think is happening. I'm going to pause the video, look at your notes, think about it, develop an answer in your head, and then compare it to what I'm about to tell you in a few seconds. All right, pause. All right, so welcome back. You have AgCl, silver chloride, turning into Ag plus and Cl minus. It's basically the equilibrium equation for dissolving silver chloride in water. So silver chloride's not very soluble, meaning if you put a bunch of this stuff in water, only some of it dissolves. It eventually gets to equilibrium. So if I tell you that this chemical reaction right here is at equilibrium, what does that mean? And all I'm asking you to do is to interpret that using some of the new vocabulary you learned, like, say, the definition of equilibrium. So here's what I would say. If you're thinking about rate, that's the easy one. The rate at which AgCl breaks down into Ag plus and Cl minus is equal to the rate at which Ag plus and Cl minus come back together to form AgCl. In other words, the rate at which the compound breaks down into its ions is happening at the exact same rate as the ions coming back together to form the compound. So, what does that mean for concentration? That's the tricky part. So if you know that the rate of the forward reaction is happening at the same rate as the reverse reaction, then the amounts or the concentrations of these two things should be constant. So the amount of AgCl solid that I have will stop changing, and the amount of Ag plus and Cl minus ions will stop changing. So concentration is constant, the rate is equal. All right, so let's try one more, then we'll do an exit slip, and you guys are done. All right, do the same thing. I'm going to pause the video now. Try to do the same thing for this equation. All right, welcome back. Let's try it one more time. I want you to interpret this equation. If I tell you that this is at equilibrium, what does it mean in terms of rate? And what does it mean in terms of concentration? Here we go. Okay, so if this is at equilibrium, the rate at which N2 and H2 turn into NH3 is equal to the rate at which NH3 turns back into N2 and H2. In other words, to go back and tie in some new vocabulary, the rate for the synthesis of NH3 is equal to the rate for the decomposition of NH3 into its elements. So the rate of the forward reaction equals the rate of the reverse reaction. What does that mean for concentration? Let me pause it. Sorry about my crazy dog. What does that mean for the not the rate, we just talked about that. What does that mean for the concentration? So if the rate of this turning into this equals the rate of this turning back into this, then the concentrations of these will be constant. The amount that I have of my reactants will stop changing, and the amounts of the products that I have will stop changing. So if the rate of the forward and reverse reactions are equal, then the concentrations of my reactants and products are constant. They stop changing. Does that make sense? I hope so. So let's see. I'm going to ask you guys in an exit slip in a minute to do that. Our objectives for the day were to have a definition of equilibrium and to interpret it when you're looking at a chemical equation. So let's see if you guys can do that. Here's your exit slip. I will post this in a Google Doc. I imagine this is a lesson you might want to watch again, maybe watch those videos again. This is not easy to understand, but I'm going to ask you guys to try to do this in your exit slip. So jump over to Google Classroom, go to the Google Doc, post your answer to this question on your exit slip and click Turn It In, and feel free to watch these videos again. All right, guys, we will see you tomorrow.